Today, I want to show you a calculus trick that can genuinely change the way you do integration problems. This trick is often associated with the book Elementary Analysis, The Theory of Calculus by Kenneth Ross, and many calculus lovers call it a life-changing integration trick because once you see it, you might start using it everywhere. Now, this is the usual way we perform integration by parts, right? Suppose we want to integrate log of x plus 3. The standard approach is to rewrite it as 1 multiplied by log of x plus 3, and then apply integration by parts. Most students take the antiderivative of 1 as simply x, so they get x multiplied by log of x plus 3 minus integral of x divided by x plus 3. And now, the remaining integral starts looking messy. This is where we now have to perform more algebraic manipulations, right? But here comes the interesting observation. Antiderivatives are never unique because we can always add a constant to them. For example, if x squared divided by 2 is an antiderivative of x, then x squared divided by 2 plus 5 is also an antiderivative. Both are equally correct because constants disappear during differentiation. And this small thing is exactly what makes the trick so powerful. So now, let us apply the Ross trick. Instead of choosing just x as the antiderivative of 1, remember that we are allowed to add any constant we want. So instead, let us choose x plus 3. Now apply integration by parts again. Suddenly, the integrand during integration by parts disappears, and it becomes x plus 3 divided by x plus 3, which is simply 1. Now, integral of 1 is simply x. Therefore, the final answer becomes x plus 3 multiplied by log of x plus 3 minus x plus constant. Wow, that is indeed super cool. Now let us move to another example where we want to integrate x multiplied by tan inverse of x. Most students begin normally by choosing the x as first function and tan inverse as the second function. Then integration by parts gives x squared divided by 2 multiplied by tangent inverse of x minus integral of x squared divided by 2 multiplied by derivative of tangent inverse, which is 1 divided by x squared plus 1. And now the remaining fraction looks unpleasant because simplifying it takes extra work. But again, instead of choosing only x squared divided by 2, let us cleverly choose x squared plus 1 whole divided by 2. We simply added 1 to this x squared. Now look carefully at what happens next. During integration by parts, the numerator x squared plus 1 cancels perfectly with the denominator x squared plus 1. So the horrible-looking integral suddenly reduces to the integral of 1 divided by 2. That means the answer immediately becomes x squared plus 1, whole divided by 2 multiplied by tan, inverse of x minus x divided by 2 plus constant. Compare this with the longer traditional solution. Once you see this pattern, many difficult integration problems start looking much simpler. Now let us try one slightly more advanced example. Suppose we want to integrate tangent inverse of square root of x plus 4. Again, we rewrite it as 1 multiplied by tangent inverse of square root of x plus 4. Its integration by parts will give us this result, right? Now, when we differentiate tangent inverse of square root of x plus 4, using the chain rule, the denominator eventually becomes 1 plus square root of x plus 4 whole squared, which simplifies into x plus 5. This times 1 over 2 times square root of x plus 4. Now this observation is the key idea. Since we know x plus 5 will appear in the denominator later, we cleverly choose x plus 5 as the antiderivative instead of just x. Now, after applying integration by parts, the denominator x plus 5 cancels perfectly with the numerator x plus 5. So, the complicated-looking integral collapses into a very simple integral. This is straightforward because the integral of 1 divided by 2 times the square root of x plus 4 is simply the square root of x plus 4. So the final answer becomes x plus 5 multiplied by tan inverse of square root of x plus 4 minus square root of x plus 4 plus constant. This is simply out of the world. If you enjoy